everyone. This next video is on linear probing, which is another method of collision resolution. As you recall, we have already covered bucketing and chaining, and both of those were closed addressing collision resolution methods. And what that meant was that effectively at every location, you had many things that could be, at every index, you could have multiple records. And in open addressing systems, that is simply not how it works. At every location, at every index element, there is only one record, okay? So when you have a collision, you can't put two different records into one location, one index. So instead of saying, oh, it has to go at hash index, you start by saying it should go at hash index, but if it's not available, we'll take the next spot over. That's pretty much open addressing in a nutshell. Now, the definition of what next means, that's a little bit dependent. So with linear probing, linear means like basically one at a time going up in a line, right? So linear probing means you start at a certain index. If that's not available, you go one index over. If that's not available, you go one more index over, and so on and so on. Other than linear probing, there is also quadratic probing, which is in the notes, but we're not really going to cover it, to an extent, but it is in the notes if you're interested. It's basically linear probing, except that instead of going one over, you go one squared over instead of going, and then and if that spot's filled, instead of going two over from the original, it's two squared over. So so the progression is one over, then four over, then nine over, and 16 over. And there's actually reasons to do this, but there's reasons to do it, but at the same time, it's sort of, I think the research says that it actually doesn't really help in the overall performance that much. So, you know, there's ideas and then everything else gets in the way, right? So don't worry about quadratic probing or the other one, which is double hashing, which says that, okay, we use a hash function to pick the first location. If it's available, great. If it's not, what we're going to do is we're going to calculate a second, using a different hash function, a second hash index. And what that second number is, that second hash function will do, is you basically use that number times a multiple to basically pick the next location. So it's one times hash function of key, hash function two of key over, two times hash function of key over, and so on. So they're kind of more elaborate schemes of saying next, but effectively move it into a different location is what open addressing does. Now, there's even different ways of implementing how to do open addressing. So we're going to actually spend some time on it. We're going to start with the basics, and then we'll talk about like when we actually implement this. This is kind of important because effectively, when we actually because your second assignment is actually on linear probing. So you're going to want to pay attention to this video, and in particular, how you might actually implement a linear probing hash table. Like what are the different methods, and what are the consequences of those methods, and so on. And we're going to talk about each of those in turn. So the basics is very simple. You use the hash function and you say, okay, try to put an index X. If that spot is already taken, put it one over. If that position is taken, put it one more over, and so on. Treat the entire array like a big circle. So if you happen to say, if the original index was, say, cap -1, which is the end of the array, the next one over is at array index 0. Just like when we were doing queues, when we were doing array queues, that's the same idea. We treat the entire array like a big circle, and we simply say, at the end of the array is the beginning of the array. Keep going around until you come back around, right? So that's how it works. Okay, so let's start with our original example. We're gonna have to change things up to make things, to talk about some of the other ideas that we have to have. But let's start with the first example, okay? Now, this is the original example that we had used for the other list, the other collision resolution methods. Let's take a look at how we would store this according to linear probing instead. So with linear probing, the first value, 15 square, is going to be stored at element 5. It's available, it's open, so we simply put it there. So 15 square goes here. Now, the next one, negative 18, it's supposed to go at element 8. Element 8 is also available, so we put negative 18 and triangle into element 8. The next one is 10. 10 goes to index 0. That one is available, no problem. So we put 10 and the star here. And the last one is 25, and of course we have a collision. So this spot is already taken. So instead of putting it like as something down here, like a second dimension, we don't do that in any of the open addressing systems. We simply put it at the next available spot. In this case, that would be right here. So with linear probing, you simply put it beside where you want it to go if the original spot is taken. Now, obviously, this will have an impact on everything that we do because now we have to, when we look for things, we can't simply say, oh, okay, go to index 5 and look for 25. We can't do that because if we were to do a search now and we just simply use the hash function, it would say, look here, right here. Is that 25? No. And if we stop right there, we would never find 25, even though it's in the table, right? So we actually have to change how our sorting algorithm works, or sorry, how our searching algorithm actually works. We have to alter it a little bit to make it actually function properly for this particular example. And there are different ways of doing linear probing, and I'm going to show you both ways. So I'm going to show you method number 1. Okay, method number 1 is really simple. Every spot for every index, we keep track of whether or not that index has something or not. Now, and that's it, just empty or not empty. Now, there's different ways that you could implement this, okay? Now, in the drawing, it looks like I have records at every location, right? But in reality, we can't really distinguish a record that is there versus a record that isn't there. So what we could do is our record has to have like a key and a value, right? We know we have to have that within our record, but we can also store another value in it that says empty, right? Empty, like is it empty? And that's just a bool, and it will let you actually say, oh, okay, if is empty is true, it's not really there. That like so I can test that field to see if that object actually exists or not. Alternatively, if you don't want to do that, one of the things that you could do is you can make this an array of pointers to these objects and simply say so in other words, instead of having an array of records, you have an array of record pointers. And if the pointer is a null pointer, then it means it's not really there. And if the record points at an actual record, it is there. And this is actually a method that you can take a look at how the implementation works. If you look at simple table, when you study the simple table code for assignment 2, you will actually see that that's actually how it's declared. It's actually declared as an array of record pointers as opposed to an array of records. And the fact that a pointer is that the pointer is null indicates that it's not actually there. And if the record is there, then it's not null. So different ways to do it, and there's no one way that you have to do it. It is simply a matter of preference, really. So how do you do it? Entirely your choice. There is no definitely do it this way kind of thing. Okay, and in fact, there's a third method that you may actually choose to do. So, but let's talk about this one first. Okay, so with this particular method, we have to make a couple of changes to our functions. So let's take a look at how we would actually write, like what are the steps to each of our functions. Okay, so for insert, now this assumes that we know that the record is definitely not there. How did we find out? Well, we did a search or something, but somehow we already know it isn't there. So for insertion of a key value pair, we start by effectively calculating get hash index. Okay, so we start by saying start is equal to get hash index. Well, actually, let's start with this. So we calculate hash value. Hash value is equal to, of course, the hash of the key, which then allows you to calculate a hash index, which is equal to hash value mod capacity, right? Which gets you the index. And then what we do is we simply say, okay, let's take a look, and if array sub hash index is empty, put it in. Okay. Now, if it's not, okay, find loop to find empty spot. Okay, and then put it into empty spot. Okay, so we basically just start the loop, start at hash index. Okay, you're not starting from the beginning of the array, you're starting at hash index. And you say, okay, is this spot empty? Yes, no, no, go to the next one. Is this spot empty? Yes, no, go to the next one, and so on until you find it. Now, your function for update is a little bit more complicated because you're doing both a search and a modify at the same time. Like you're doing insertion and modify at the same time, like you don't know if it's there. But it's not actually that bad. What you do is you just simply see, is it already there? Like just look for it first, right? And either you find it, or if you don't find it, you actually, if you do your search, if you don't find it, the way that your searching actually stops is you look for the first empty spot. So either you find it or you find where it's supposed to go, right? So you can actually do it in one go. And we'll talk a little bit more about that in a moment. Um, so let's let's talk about searching. So this is insertion. Modification is pretty straightforward. It's pretty similar. Let's talk about searching, because searching is really important to any hash table. You can't talk about hash tables without talking about how fast the search is. Now, searching is actually simply this. You start off by saying, okay, I'm going to look for, oh, sorry, searching doesn't have a value, it just has a key. You start by looking for the key, right? And then you say, okay, we start at this hash index. And then you basically loop until either array loop starting at hash index until either A, you find the record with the key you want. Now, remember, you're not looking for the hash value, you are looking for the key. So just because your hash index is calculated from your key, you actually have to look inside the record and say, is this a matching key? Because that's the important part. So you have to say, so you look at array sub I and you say, is the key in this particular record matching the key I'm looking for? If it is, then you found it. Now, you loop until you either find the key or you get to an empty record. If the record doesn't really exist, so if you had at some point put in a record with exactly that key, then it would be there. It would be somewhere before you hit an empty spot. The moment you hit an empty spot, you need to stop. Okay? Now, this is really important. Okay? Really important note. Super duper important. Not stopping when you hit an empty spot will cause the table to behave terribly. Okay, so if you keep searching, okay, if you go past the empty spot because you couldn't find it, right? Keep going. go until you can't find or you come all the way back around. That should never occur. Okay? You have to stop as soon as you hit an empty spot. Okay? When you hit an empty spot, that is when you stop looking, not when you go all the way around. Okay? It's not better. It just means you're trying to cover up a different bug. Okay, so if the tester says, "Oh, I tried to look for something and it should be there, but it wasn't," and you end up searching the whole array for it, that just means you're trying to cover up a bug. That's not better. Okay, if you write your code properly, when you find you will either find the record before you hit an empty spot, or the record really isn't there. So either way, you need to stop. So get to an empty spot and then stop looking. Stop looking either when you find it or get to an empty spot. Either way, you have to absolutely stop. Stopping is essential for the speed of this particular data structure. You cannot keep going, okay? Hit an empty spot, stop, done. Okay, so this is effectively how you write the search function. This is how you do it with it for insertion. Modify is basically modify is pretty much like insertion. It's not really all that different. You're going to take the same basic idea, right? Okay, so you're going to basically, actually what you're going to do is you're going to find location of record, okay, which is basically the search algorithm. Find the location first, and then update the value if record found. Find location of record with matching key, and then update the value if the record is found. That's pretty much modify. So these ideas are pretty simple, pretty straightforward, I think. The hardest function to write with linear probing is not these ones. These are relatively simple. The hardest is when it comes to removal, and we'll talk about that in a moment. But that's pretty much how you do insertion. Okay, so here we've inserted 15 and we've inserted 25. Okay, so very quickly to see how the searching would work. If I try to search for 25, what I would do first is I would actually start by saying, okay, 25 is supposed to go into element 5. So I'm going to start looking here. Is this thing 25? Well, no. So I'm going to move over to the next one. Is this thing 25? Well, yes. So we're done, right? Now, if I were to search for the key of 35, which doesn't exist, okay, my hash function on 35 leads to 35. Then we do a mod, 35 mod 10, which gives me index 10. So, index 5. So 35 mod 10 gives me index 5. So I'm supposed to start looking for 35 right here. Now this isn't 35, so I go over to the next one. This isn't 35, so I go over to the next one. Now this spot here, this is empty. So I don't have to keep looking, because if at some point I had inserted 35, it would actually be in the spot. The fact that this spot is empty says I'm done. There's no possibility that 35 would be here. If I had at some point inserted it, it would actually have to be in this exact spot. So we stop the searching at this point. We don't continue our search for 35 because there's no point. It's never going to be there. So stop searching. Okay, and that's really what this part. That's really what the searching algorithm says. When you hit an empty spot, you have to stop. Okay. So now let's take a look at some issues that actually arise from this. So that seems pretty. That actually isn't terrible. You just go until you find it, right? Or go until you hit an empty spot. Now, what would happen if the following occurred though? So let's say that I remove 15 from my So let's say that I wanted to remove the record with 15 as the key. Now, if all I did was say, oh, okay, I want to remove it, so that just means I make the spot empty, right? Easy. I mark it as empty somehow, whatever method you represent as empty. And now it's gone forever and we're good, right? Now, we have a problem. if I remove 15, 25 won't be found anymore. Won't be found if we just mark spot as empty. And why is that? Well, remember, our algorithm says we look until we either find it or it's empty, right? So if I was to now do a search on 25, I would start at index 5 and, oh, it's empty, so it must not be there, right? And that's a problem because obviously it's still there. I removed 15, not 25. So we have to be careful when we do our removal algorithms that we don't do that, that we don't actually have a situation where by removing a record, other records cannot be found. So what does this actually mean? What does it mean for us to actually remove a record from a spot? So removal is actually the one that is kind of tough. Okay, so let's do a remove. Remove key that remove a certain key. So what do? Well, you actually do the following. You start by saying, okay, I'm going to find the record, find location of record with matching key. That's actually the first part of pretty much every single one of these algorithms. We do the search function routine and look for the index. Okay, that's a hint, by the way. If you actually separate that concern of just like finding the correct index, okay, you can basically just make a function call in each of your functions and it would just work. Okay, find the index of the location with a matching key. If you have that function return either the index of the matching key or the empty spot that is like the correct, like the one that just follows where it should have been found, then you can make use of that function everywhere in your assignment and it'll make your life a lot simpler. So that's a hint of what you should write. Okay, make it a private function though. Now, find the location of a record with a matching key. Once you have done this, what you do now is if you find it, so if it is found, okay, now this is kind of important because if it's not found, you do nothing and you get out, right? So if there's no record found, then do nothing, get out. Now, if it is found though, we have to actually remove it. So what do? First of all, we call this spot current. Current equals location of record with matching key. Okay, mark array subcurrent as empty. So let's start with that. So we're going to start with the current being just, oh, this is the location of the record. Okay, this is where we begin, and we mark that location as empty. So basically what the picture shows. But now what we have to do is we have to look, actually, no, sorry, that's wrong. We mark this, we say, we create a variable called empty index, empty IDX as empty. So this location is the current location of the empty spot. We mark that spot as empty. So we get rid of the record. This is now an empty spot. We create a variable called current, which is equal to empty IDX plus 1. Go around if needed. So going around if needed means, you know, if plus 1 means you're at the back of, if you were at the back of the array, plus 1 means 0, okay? So make sure you, when you're doing this, you actually account for the looping of the array, okay? And remember that there is that little formula that you can use where you just like add 1 anyways, and then you do the mod on cap, okay? So that's sort of like, that's the function you should use, don't just go plus plus, it doesn't work, okay? So you start with that. Your current spot is wherever the empty spot is, 1 spot over, okay? And then what do you do after that? Well, you loop until current array subcurrent is empty. So if the next spot over is empty, you're done. You don't actually have to do this loop at all. But if it's not empty, you have to keep going. And what do you do? Okay. Inside this loop, you're going to do the following. Determine if the record at array subcurrent should be moved to array sub empty. Okay, and really what we're doing is we're saying, is this on the wrong side of our divide, if you will? And how you do that is actually by, say, asking this question, and it's a really weird way to phrase it, but what it really comes down to is empty IDX between hash index of current record, okay? Not the one that you were getting rid of, the one that you're looking at. Is it between the hash index of that and current IDX and current? Okay, so for the object that I'm looking at right now, for the record I'm looking at right now, what is this hash index and what is this current index, and is hash IDX in between those two values? Now, in between is normally a very easy idea. It's like greater than hash, less than equal to current. That's really the less than current, right? Like that's sort of the question. Except that with the wraparound, um, because you're wrapping around, you can't just use greater than less than. It's actually a little bit more complicated. You're going to have to write a function. I think the easiest way that I found to do this particular task is to actually just write a is between function that basically you pass in 3 indexes and it says, okay, I'm going to do some testing to see if I'm going around in a circle. And if I am, I'm going to do one. And if I'm not, I'm going to do another. And separate that concern, because that will actually be a lot easier than trying to code like 3 or 4 different if statements right in the body of your function. Separate that concern and it'll make your life a lot easier. But effectively, this is all you're doing. You're basically asking the question, should I move this record? If I do, move it. And move if needed. So to move a record, what you do is you basically say array sub empty IDX is effectively array sub current, right? Just do an assignment. And then you have to make empty IDX equal to current. So to move a record, you have to do a few things. You have to do that. And then you have to say, okay, well, now that I've moved it, my current IDX is actually the empty IDX. So I'm going to set that. And then we continue on and move current to the next position, repeat this algorithm, and we're done. So this is the basic algorithm for removal. Now, it's probably easier to draw than it is to write, and to sort of see where we might have problems and why this even works at all. But so let's draw some pictures and take a look at this, okay? So I'm going to redraw this. We're going to actually have to add a few more records to make this more interesting, okay? So here is my original record, okay? Now I'm going to put a few more, I'm going to do actually a few more insertions. Now it really doesn't matter what the value is, so I'm not really going to worry about trying to draw a value into this. We really only care about the keys. So I'm not really going to be too concerned about the value part. So pay attention. What you need to pay attention to are just the keys within these records. So let's begin by doing a couple of extra insertions. So this is a lot more interesting, okay? So I'm going to start by inserting the following keys. Minus 14, since we haven't done too many minuses, okay? So we're going to add these two: key value of minus 14 and also so minus 14 and also, let's see, let's do my 24, and also let's make it really bad. Let's actually, let's start with just this. Yeah, let's start with just this, and then we'll do one extra, a couple of extras after this. Okay, so so for these ones, I'm just going to add some values. And it doesn't matter if these ones have repeated values, right? So because values are not unique, so I can actually put the same value into different records. So if I have this as my beginning, when I try to insert minus 14 ends up here. Why? Because, well, because hash of key of minus 14 is 4. And index, or sorry, minus, that's wrong, sorry. My hash function was the absolute value function, right? 14, 24. So index, so the hash index, which is the modulus, hash index is going to be at 4 and 4. So minus 14 ends up here at hash index 4. And 24, if I try to insert it right after that, 24 tries to put itself into 4, couldn't, tries to put itself into 5, couldn't, tries to put itself into 6, also couldn't, and then ends up at 7, because that's the empty spot that it found, that was able to find after index 4. So let's put in 24. So 24 ends up here because this is the first available spot to it. Okay, so that is our table so far. Now clearly 24 isn't in the right place, and some things are in the right place, some things are not. So let's see what happens if we do if we remove certain things and how things get shifted. Okay, so this is our table so far. Okay, and I'm just going to duplicate this and show you what happens when we try to do a remove. Okay, so here is our table, and now we're going to try to do a remove, and I'm going to remove 15. Okay, so we're going to start by removing 15. Now, what does that mean? Well, we're going to make that the first step, remember, is we have to find it and then make it empty, right? And then we store something called the location of the empty IDX. So pictorially, it's actually a lot easier to see. So basically, it's empty. Okay. Now I do have to track some things. So I'm going to track an empty IDX. Empty IDX. Now this is where I just emptied out my spot. So this is going to be equal to currently 5. Okay. Let me move this table a little bit. Okay, I need some space down here. Okay, so I'm going to use this little arrow with an E to indicate this is where empty IDX refers to, but it's what we store is just a number. Okay, now for current is one past whatever empty IDX is, which is, so it starts its life at 6. Okay, and I'm going to represent that using this symbol for current, C. Okay, now what do we do? Well, what we now ask ourselves is, given the record right here, 25, okay, this record right here, what is this particular record's hash index? Now, we actually have this information, right? Remember, this was it. So the hash index was 5. Okay. Also, we can recalculate, but effectively we can get the hash index for whatever the current thing is. So our hash index, okay, hash index for 25, okay, is 5. So the proper location, in other words, the proper hash index, okay, in the notes they call, I use the word proper. So proper just means hash index. Hash index of 25 is going to be 5. Now, so the question you're asking is this number in between this one and this one? So is it greater than and or equal to 5, less than 6? Okay. Now, there's a way to sort of pictorially view this. What you do is you draw an arrow. So I'm going to use green here. Draw an arrow between where it is right now. This is the current location. Okay. Where is the proper hash index? That's the 5. And usually I draw it to the beginning of the thing so it's a little bit more clear. So what you're asking is E, that's this thing, is it in between these 2 points? Okay. So that's what you're asking. Is the empty spot in between where the record currently resides and its proper location? If the answer to that question is yes, and it is in this case, you're going to move this record. So take this record, move it over. Okay? So that would be step 1. Now, at this point, my record is we're okay here, and what happens next is, well, okay, I just moved it, so this spot isn't empty anymore, so obviously I have to move this thing, right? I have to move it, and I also have to move the current is actually going to go 1 over, and my empty spot is actually going to go here. Okay, so this is now my empty spot. Sorry, making a mess of my drawing. Oops. Okay, so effectively move this record over, and then now code-wise you might do this in a different order, but effectively that. You have to move your empty to where your current is, move the current over. Okay, but effectively this is what you have when you finish that step. Now, we're not done yet. We have to check the next one. So what about 24? Okay, where is 20? Oops, where is 24? And do we want to move it? So now we have a different situation. Our hash index is, sorry, our empty index is now at 6. Our current index is now at 7. And what is the proper hash index for 24? Well, that would be 4, right? So if we were to draw an arrow between 24 and its proper location at 4, ask the question, is E somewhere in between this right here, this spot right here, and this spot? Is this in between those two? And if the answer to that question is yes, you have to move it. And it is, right? So like E is in between where it is and where it should be. So we move 24 over by 1. Or we move 24 into the empty spot. Done. Now, we then advance E to where current is, and current moves over as well, so just moving these guys properly. And now we look at the next situation. So we're still doing this. Now, our empty spot is now at 7, okay? Our current location is at 8. What is the proper hash index for minus 18? Well, that one is actually at 8. So if I were to draw an arrow from where it is right now to where it is supposed to be, it's here. So is the empty spot in between where it is and where it's supposed to be? So is E, oops, somewhere in between here? And the answer is no. Visually, you can see that like this spot and where it is right here. So it's just a very tight spot, and E is right here. It's not in between those 2 points. So we're not going to move this particular record. Now, there could be another record beyond this. There isn't, but there could be another record. So again, so now we only change current. We only move current because our empty spot is still where it is. We haven't added, moved something into it. So it's still the empty spot. So we now take a look at current and we say, okay, current is now 9. So this spot is empty, which means that we have dealt with everything in what we call the cluster. So we talk about these in terms of like a whole bunch of records together forms a cluster. And we're basically saying, oh, okay, this spot's empty, so we don't have anything to move in anymore. So we're done. So this is the basic idea of how to do this particular method of linear probing. You simply say either something is there or isn't there. And then whenever you do a removal, you apply this algorithm that goes around in a circle to every single record up to an empty spot and ask, should I move this? Now, another way to look at this, the whole thing, another way to view the way this works is as follows. So let's say that I have a block of records, okay? Now, we actually call this block, so these are records that we have in general, and they exist side by side, and every single one of these spots are filled, okay? Now, we have an empty spot here, and we have an empty spot over here. So these two are empty, but this stuff, the ones in between them are not empty, okay? So, sorry, my handwriting is horrible. So I'm just going to represent this by big E. So these two E's represent an empty spot, and everything in between the two empty spots are filled. We call this a cluster of records because, you know, they're kind of packed together like a cluster, right? So what it means, the way that you sort of think about this is all of these have an index, right? So index A, B, C, D, E, F, G. Now, if I took any hash value, any key, if the index of that key happens to be one of A, B, C, D, E, F, G, any one of them, it doesn't matter which one, I would actually find it somewhere within that cluster. Okay, so if I was looking for something whose hash index was one of those indices, that A to G, I would actually find it somewhere in here. Now, if at some point I do a removal, what I'm actually doing, so let's say I remove D over here. What I'm actually doing is I've taken one cluster and I've turned it into 2 separate clusters because now, instead of having 7 things in a row, I have an empty spot in between, right? Which means that it actually changes from one big cluster to 2 small clusters, to 2 smaller clusters. Now, that's actually a good thing, by the way. Having 2 smaller clusters is good because we actually search less. So if I wanted to find something and it was in one of the first 3, I search until I have an empty spot. I get to the empty spot faster. Now, if we consider what has happened is another way to look at this is the following. Originally, when I had everything here, and I'm going to actually use some different colors over here. And I know these are possibly horrible color choices. But let's say that I have a few different things here. And finally, maybe black. I'm not sure if that's really distinguishable from the blue, but in any case, it doesn't matter. So um, if you're looking for something whose proper hash index was supposed to be A, um, what we do know about that is that anything that was supposed to be an A either is here, is from A all the way up to the empty spot, right? So this is A. Anything that should have gone to B, okay, like the proper hash index being B, starts at B and goes up to the same spot. For C, it's the first spot it was available was at C and it goes all the way up to the empty spot. And if the proper location was D, then it's D all the way to the empty spot, and so on, right? So basically what it means is that anything that I could have put into D, it might be at D, it might be at E, might be at F, might be at G, all the way up to the empty spot, it's a possibility. Whereas for A, if something was supposed to be at A, it's either at A or at one of the spots all the way up to G. So depending on how close you are to that empty spot, the search is actually slightly different. Now, when you remove something from your array, what you're doing is you're actually start taking that one cluster and you are making it two separate clusters. So instead of doing that, you're saying, oh, okay, really, they're two separate entities now. So anything that should be at A is either going to be here all the way only up to that point. Now that's good because now instead of searching 7 spots, I only have to search one spot, right? Or sorry, 3 spots. So that's actually a good thing. So A is now here. Okay, B is now here, and C is even better. Now, so removal can actually make things faster because you have now smaller clusters. Instead of one big cluster, you have two smaller clusters. That's a good thing. Now, unfortunately, though, after you remove something, um, some of these things over here might actually be in the wrong place. They might be in the wrong cluster because originally we said that something that was at B could be anywhere along here. So perhaps this guy right here at the very end where it's G, maybe that should have been at B, right? So the idea is to effectively say, look, great, we have removed something, we can have two smaller clusters, but what we need to do is we need to make sure that the things in this cluster actually belong in that cluster. It shouldn't belong to the first cluster. So that's what we're doing is we're basically testing, should this thing here really be here? Or should it go back with the first part? And that's what you're doing with that whole checking, like, oh, is it between proper hash index and current location? That's what you're doing. You're basically saying, is the empty spot in the right place? And if it is, great. If it's not, you do an exchange and you say, okay, this now is in the first cluster and the empty spot is now here. So that's really what you're doing with a removal. Is you're basically taking one big cluster and turning it into two smaller ones. And depending on how bad this cluster was formed, it could be two equally sized smaller ones. It could be very lopsided, and that's okay. All right, so this is effectively what you're doing and the reason why you do it. Okay, now the good thing about this is that, so the bad thing about this is that it's actually, the is between function is actually a little bit tricky to write. It's not terrible, it's just you have to work through the logic of it. But it's actually not that terrible. You just have to write that. The idea I don't think is particularly hard. It's just you just have to deal with it. That's all. Okay. But there is actually a method, and some students find this second method of representation a little bit easier to follow than the first method. So the first method works, and I think there are some. So a friend of mine says that this method actually works out faster. Like when it comes to performance, this one's the faster performer. But um, I think for a lot of students, I think that they find this a little bit hard to understand, to get right. And mostly it's because the one is between function is hard to write. And it's also because, and oftentimes I find that it's also because you try to write your logic right inside your remove. Don't do that. Separate the logic, and it will make your life a lot easier. Okay? Write a function that all it does is it tells you should you move it. That's it. And it's a lot easier to implement than if you try to code it right inside your remove, because the logic gets pretty, it's not hard. It's like 4 or 5 if statements, just that it's like nested and convoluted. So anyhow, let's talk about the other alternative. So the alternative way of representing linear probing tables is to use an idea called that I don't know if this is the proper term, to tell you the truth. Um, this is what my friend calls it, and this is what I found in other literature. So I'm like, okay, we'll go with it. Tombstoning. But effectively, this is what you do in tombstoning. So remember when I said that when you represent your record, you basically say, um, this is how you either say it's empty or not empty, and that's it. So with tombstoning, you actually have 3 different statuses instead of 2. Okay, so with this first method, the non-tombstoning method, it's either empty or not empty. That's it, empty or not empty. With the tombstoning method, you actually have to store a status that has 3 possibilities. So every record not only has the record in it, every array element, but it also has to store a status. Okay. Now, what is the status? So 1, 2, 3, 4, 5, 6, 7, 8. Oh, missing one. 9. Okay. So the status, there are 3 statuses. There's still empty. There is O for occupied. Excuse me. And there is also, I'm going to use an X for deleted. Now, whether you use exactly these symbols or whatever, that's up to you. It's really just 3 different statuses, so you can't represent it with a bool. Minimally, you have to use a char, because like you have to represent 3 states of an object, okay? I guess you could use bit fields, but let's not do that. But in any case, empty, occupied, deleted. You have to be able to represent all 3 states of any particular record. So when the object is first created, we mark every record as being empty. So if we use the same example as before, every record begins its life as empty. Excuse me. Video is too long. My throat's drying out. So let's put this table back in just to remind ourselves what we're putting in. So 5 goes into the same location. So the basic algorithm is actually not different. We take the 5, the 15 goes into location 5. The -18 goes into location 8. Okay. The 10 goes into location 0. Okay. And the 25 goes into location 6 because 5 was already occupied. So this part is actually exactly the same as before. Now, when we put something in, we change the status, which I forgot to do. If the spot is occupied, we change it to O to say it's occupied already. Okay. Now, the good news is that it makes searching pretty easy. You search until you hit empty. That part actually doesn't change. What does change is what happens when you do, what happens, we have to actually modify both the insertion as well as the deletion algorithm slightly. So the searching is you start at the index, search until you hit the empty spot, done. Okay, or you find it. Either condition, you stop. Now, what what about insertion? How does the insertion change? Or actually, let's do deletion first, because that's the that's the reason why we're doing this. When you do a deletion, what you do is this. So let's say that I was getting rid of 15. Instead of marking it as empty, you actually change its status to deleted. So it's not empty, it's deleted, which is different. Okay, deleted and empty are two different things. Okay. Now, what does it mean for something to be deleted? Our searches starting at the location until it hits an empty spot, right? So if we were to use this method, and I was looking for 25, I don't move 25 at all. What I do is I start at the 5 and I say, oh, okay, this spot is deleted. So I have to actually keep looking. I can't stop. I then go to this one. Oh, okay, I find it, right? If I was searching for 35, I would actually start at the 25 at the 5 and say, "Oh, okay, that 35 should have been at 5, but it's not there, so I go here. 35 should be there, but it's not there, so I go over here. This one is empty, I stop." So the algorithm is still search until empty, but deleted is not empty, so don't stop when you have deleted. You have to keep going until you hit the empty spot. Okay? So searching for 35 is actually going to mean searching until the 7, not stopping as soon as you delete it. Okay, you have to keep going until you hit an empty spot. That's the important part. Now, obviously, this is actually pretty easy to implement because all I have to do is change the status, right? On insertion, though, it's a bit different. So let's say that I did the deletion on the 15, and then I ended up trying to add something else. So let's say that I tried to add um, let's say that I tried to add 35. Okay, 35. You know, doesn't matter what the symbol is. So the hash of that is 35. The modulus takes it to 5. And so where would I put 35? Well, I would actually start at index 5. Now, if the spot was deleted, it means it's not being used, right? So I can actually take 35 at this point and put it where index 5 is. So this is what I would do instead of what I would alter for the insertion algorithm. For insertion, when you're looking for the place to put something, you actually treat deleted as being a place where you can put something. Okay, when you're searching, you search until the empty spot. But if you were doing an insertion, when you're doing the searching, you actually don't stop at an empty spot. You stop on a deleted spot, the first deleted spot or empty spot, whichever comes first, right? So when you're looking for a place to put something, you simply start at the location, and as soon as you find something that is not occupied, you can put it in there. That's how the insertion algorithm would end up working. So it's a little bit different, but most students, I think, find this particular algorithm a lot easier to understand and a lot easier to implement. So you may want to consider doing this one instead because it's actually fairly straightforward, um, fairly easy to do. So consider doing it. Okay. But according to my friend, this one has algorithmic, this first one actually runs faster. I can see that because right now, if you delete something, you don't turn one big cluster into a smaller cluster. You keep the same size cluster effectively, right? So you could end up actually creating a whole bunch. If you do a lot of removals, you could actually end up creating a whole bunch of empty spots, like deleted spots, but you still have to search through them. So might not be the best implementation, but it actually, for the most part, most people find that this is much easier to implement, much easier to understand. Do I care which one you do? No, pick one. Okay. So that's pretty much it. If you have questions, we can bring it up. We can discuss this further in class, and I think I'll just draw it based on the questions that I get. But hopefully, this will help you get started on your assignment. That's it.